but the skill level of people who practice in that room kind of varies throughout the day. So you might have some really nice music now, and you don't know what you're going to get to later. All right, cool. Let me go ahead and get this going. All right. Hello, everyone. My name is Dr. Samuel Eng, and I wanted to do a quick poll before we get started because I might adjust this lecture a little bit. I created this lecture in mind with the idea that all of us have had a little bit of programming experience before. Is there anyone here who has zero programming experience in this room? One? Okay. Stop me if we're going a little too fast. So we're going to take a few things for granted here. Generally, we're going to work in a very straightforward way today and try to keep things as simple as possible. But I might throw out a few concepts you aren't quite familiar with yet. But okay. Oh, okay. Yeah, just getting those credits, right? Yeah, so we'll kind of see that I never know quite what the experience level of individuals is going to be when we do these presentations. So we'll just kind of play it by ear and hopefully have some fun. So yeah, today's lecture, we're going to do a really brief introduction to creating games with some tools known as Love2D and the programming language Lua. Quick apology for this. I actually thought this presentation was going to be on Friday, and so there's a couple things in this lecture I wanted to add, change, polish up. It might be a little bit messy, so bear with me for a bit. Our goal is to prototype today the classic game of Pong, so 2D tennis with 2 paddles and a ball, in roughly 100 lines of code with these tools. Quick introduction to me. So who am I? I'm Dr. Samuel Eng. This is my second year teaching at UTSA. I teach a lot of the game development and game development-centric courses. So game development, we have a new class called Fundamentals of Game Programming, along with graphics, object-oriented programming stuff, programming to some of the intro courses. I have a personal research focus here at UTSA involving virtual reality and motion sickness. So how can we modify VR software to make it more accommodating for a wider variety of people? In game dev, I have a background as a solo developer, which is kind of a unique perspective and doesn't make me kind of ideal for talking about the industry in general. I kind of just work on my own. I'm used to kind of doing everything myself, for better or for worse. I released an early access game a couple of years ago called Dead Eye Deepfake Simulacrum, which generated 99% positive reviews on Steam, was ranked 28th on the Hidden Gems list, grossed about 100K in revenue since releasing, and it's hopefully going to get to 1.0 by the end of the summer. We'll see if I can finish it up by then. But this is basically my background. I want to start off today, before we get started with our tools, with a crisis that is going on in the world of programming. And I wanted to run one more poll here, because I don't want to repeat myself too much, but are any of you currently in one of the game dev classes with us right here? One of you. Okay, so I apologize if you've heard this tiresome rant before, but we're going to do it again. I love giving it. So most of us, it seems like everyone but one of us has some experience with programming. Who knows how we can like print something to the terminal in a programming language? Like, raise your hand if you know how to do that. Yeah. Yeah, yeah. All right. You know, what's a language you know? What's a programming language you know? C. And how do we print something to the terminal in C? Printf, right? C as a language comes with a function called printf. We call it. It writes some text to the terminal, and that's good for basic output, for debugging, for all those things. Really basic operation. If we're working in another language, so this is Golang, we're going to have something really similar. Programming languages have largely figured this out. We call format.println. We put a string literal, and that is going to show up on the terminal. And like virtually every programming language is going to come with some way in order to do this. Okay, so I got another question for you. So you know C, and it sounds like you know C pretty well. You know how to print something to the screen after all. How do we perform the basic operation of drawing a square to the screen in C? Not quite sure, right? And you know, if I asked that question to really any of you, I'd probably get a reaction that looks something like this. You know, gulp. And this is the crisis of graphics, in my opinion. For some reason, this basic operation of just drawing stuff on screen is really, really limited. It's hard to just draw a triangle or a square. There's no easy answer to that problem most of the time without relying on something huge and gigantic to help us. You have a couple of options for drawing things to the screen. So the first option, if you're really serious is using what's called a graphics API. A graphics API is basically a piece of software that relays information from you and your program to the graphics processing unit on your computer, which completes very quick floating point operations. And there are lots of different options here. So if you want to work with OpenGL, it's kind of the tried and true, the gold standard, the OG. It's a little slow and old at this point, but it's widely supported. If you want to draw a triangle in OpenGL, it's about 300 lines of code. 100 lines per vertex on that triangle. OpenGL is also, in my opinion, a really atrocious API to work with. It's built without modern hardware in mind. A lot of it is like hidden away in drivers and stuff, so it's very hard to debug. We next have Vulkan. Vulkan is an updated graphics API supported by AMD and some other companies that's meant to be more modern, work better with modern hardware. If you go by their GitHub example, drawing a triangle in Vulkan is about 1,200 lines of code, so it's gotten worse. Somehow this is the best option if you're going with a pure straight graphics API. So drawing the second triangle on screen, that's only going to be 1,201 lines of code after that. But just setting this stuff up takes an enormous amount of work. There's an enormous amount of boilerplate of settings to configure and stuff like that. We've also got DirectX from Microsoft. It's Microsoft slop, who cares? DirectX has like notorious issues with backwards compatibility and whatnot. We've also got Metal, which is Apple slop, who cares? I've never even looked at it before, so it might be great, but I don't know. Another option we have are game engines, and game engines are like better than ever. You can pick your poison. They are free. They are super widely supported and worked on and boosted by these giant mega corporations that pour tons of money into them. So you've got Unity, you've got Godot, you've got Unreal, GameMaker, tons of other stuff. Game engines provide you a lot out of the box. They won't just let you draw a triangle or a rectangle on screen. They'll come with tools for AI and visual scripting and 3D modeling and level design. They come with so much out of the box a lot of the time. But it's kind of a shame to have to buy into this huge ecosystem just to like draw a square. Like sometimes we're not trying to do something so complicated that requires all these tools, and we need to download some big, multi-gigabyte sized software suite from the internet. Engines can also hide a lot of what is going on under the hood, and it can kind of force you into certain ways of thinking about game programming that are not as universal as they might appear if you've just started with a single engine like Unity or something. Now, a solid compromise between this stuff is something called Raylib, which is a graphics library built on top of OpenGL. It's really elegant. It feels great to work with, and this is what we teach the current kind of intro to games programming course in. It works virtually across all platforms, and it comes with bindings for basically any programming language you can think of, including Go, which I mentioned earlier in the slides. Really any language you can think of. If you're programming in like Beef, most of you probably have never heard of Beef before, you can do that in Raylib. If you're programming in like Fortran for some reason, somehow there are Raylib bindings for that. It's very widely supported. It's great. It's the community pick. We use this for the Intro to Game Dev class, but today we're going to explore another option, which is arguably a little bit more user-friendly, and we're tinkering with the idea of making the new intro class use this tool instead. That is Love2D. So Love2D, also known as Love, is free open source framework for making 2D games with a language called Lua. It is designed to be beginner friendly while still offering some powerful and useful features that allow you to make serious games. And with it, we're going to be able to make Pong today in just about 100 lines of code. It's actually 112. I needed some extra code to draw the score stuff on screen, but it's almost there. We can pretend it's 100 lines. Love2D was the toolset used to make the game Balatro, which you might be familiar with. Balatro is a poker-based roguelike game which generated a whole bunch of buzz. Another semi-popular game on Steam called Moonring, which is a top-down 2D roguelike, which is really awesome. It's free to download. I recommend checking that out as well. Love2D has the benefit of some kind of like existing heavy-duty games in its back pocket. I'm always a little bit hesitant to use a new engine or a new set of tools until there's some kind of concrete proof that the engine is capable of rolling out professional quality software. Love2D has some limitations and some weird issues, and I've got some personal gripes about it, but it is undoubtedly capable of making real games, so it at least passes that test. Love2D uses the Lua programming language. Lua is a lightweight, high-level programming language, primarily for embedded use in other applications. Something great about Lua is that if you have an existing code base written in C or C++, which are fast languages but can be a little bit hard to use, you can then inject basically some Lua, which is easy to write into that and get it working together. So Lua is often used to configure games and various pieces of software. So if you ever played like Roblox or something before, you can use Lua scripting in Roblox to create custom user-made content. If you've used NeoVim as a text editor, NeoVim, all of its configuration is done in Lua, and this is usually the purpose of Lua as a language. It is a really simple language, like an almost radically simple language. It has no strong types, so you can mix and match data kind of at will as you want. It is interpreted, not compiled, which makes it kind of slow, and for a lot of people, this means Lua is kind of a non-starter for a games programming language. Typically, we want something compiled so we can check for bugs and so that we have that level of performance that's usually needed. Sometimes working with an interpreted language is nice, though. If you've ever opened up Godot and worked with GDScript, which is their proprietary interpretive language, it's nice that you don't have to wait for things to compile ever. You can click a button and things are instantly running. Now, when you run into a bug that only appears after running your game for a certain number of hours, because it's interpreted, that can be a little bit annoying. But it's an interesting perspective on games development that I at least wanted to explore a little bit personally before introducing it into a class. Though it is interpreted, Lua is still fairly quick, so it's not going to be as fast as like C or these other applications programming languages like Java or Scala or things like that. But it's a lot faster than something like Python. It's very, very fast for an interpreted language. It's also really strange. It's not what we're used to in a whole bunch of ways. Lua infamously has 1 indexing instead of 0 indexing. So to access the first element of an array, you would use 1. Thankfully, we're not going to need to do that for today's example. We're not going to get too deep into the language, but those are the sorts of things you kind of need to accept if you're working with Lua. Okay, duplicate slide there. So hopefully you have Love2D set up. We don't have time to go through the whole setup process today. There should have been like a link included in the flyer. If you were unable to do so, then it's fine. Feel free to just follow along. This will be like recorded and live streamed and stuff. And another great thing about Love2D is there are tons of tutorials out there that are going to do a much thorough job than we can do in this one hour, now 45 minutes that we have left. I've also set up a few things specifically on my end. This will change how I'm like running my program and stuff. So if you see me doing an odd thing now and then, this is just kind of a shortcut I've included. You don't necessarily need to have that yourself. We're going to keep things really simple today, and we're going to code in an extremely straightforward manner. If we're making a more complicated game where we want to reliably recycle our work, we would put more effort into dividing our code up between files and making sure we don't have duplicate pieces of code running, condensing things down into nice little functions and stuff. Today we want to keep things simple, really straightforward. We are just going to code this from start to finish, not worrying about that stuff. Maybe if we do a future lecture where we create like a classic roguelike or something in Lua, ooh, that sounds rough, then we could maybe get a little more advanced with these organizational practices, but we're keeping it simple today. All right, so let's make a Love2D project. How do we do this? I'm going to go and pop out of here and head over to my hard drive. And I've got a folder here with all my Lua projects. I'm going to go ahead and create a new folder here, and I'll just call this something, Meepus. I'm going to go ahead and open up this code here and pull up a brand fresh new window. I'm going to drag the Meepus folder so that I trust the authors. The authors are me after all. And in VS Code, I'm going to go ahead and create a new file here with the new file button. I'll call this main.lua. Lua files have the .lua extension, and unfortunately, the biggest problem with Lua is that it doesn't have like a cute mascot that regularly goes with it. The mascot for Lua is this little planet with a moon going around it, which is kind of cute. I would have preferred it had like a little dude or a little gopher animal or something. That that's the true sign of a good programming language. Okay, so we got main.lua here, and let's go ahead and find Love2D on our computer. I'm going to right-click and open the file location of this. So if you locate the Love2D executable or shortcut, what you can do after this point is take your folder containing all of your Lua code and just drag it in to that shortcut, and it should pop you up with a window. And if that happens, you are good to go. Now, our file is literally empty, so nothing is going to be happening in our game at this point, but we at least know that the program is working. We can run our code if we need to. I mentioned that I've added a couple things on my personal setup. The main thing is that, I've added love to my path, meaning if I want to run a Love2D game, I can, within the terminal, just type love dot, and that'll open up a window from here, which is a little bit quicker for my personal needs, but you can just drag it in for now. We won't worry about setting all that stuff up. Okay, So with that out of the way, we know how to make the basic project really, really simple, which I love. I hate things where we need to open up like some big editor like Visual Studio and like have it link all this stuff together. Now we just put a file in a folder and we're good to go. Let's talk about the basic Love 2D program. The basic Love 2D program with 3 functions. And here's the first kind of odd thing about Lua you might not be used to. Lua is not going to use curly braces like we do in Java or in C, which are the 2 languages we stick with most of the time in CS. Lua is going to use white space and indentations. And this is how we create functions in Lua. We use the function keyword followed by the name of the function. In this case, we are borrowing functions from Love2D, so we're going to use love dot on there. And we need to declare 3 functions to get our program running. These are called load, update, and draw. And they each have a different purpose. Load is in charge of getting things ready, setting things up, loading resources. So if we had textures or audio files that we needed to load into memory before our game starts, we would handle that in the function here. We're just going to do a little bit with load today. We don't need to worry about it too much. The next is update. This is going to be in charge of managing our game logic. So every single frame of the game where we refresh the image on screen, we're going to go through, we're going to change stuff, move things around, make sure everything is working. And then finally in draw, we're going to handle the rendering. This is when information is actually going to be taken from our game state and displayed to the screen on the pixels of our window. Okay, so this idea of frames and refresh rate, what am I talking about here? This might be some terminology we're not super familiar with. When we move stuff around on the screen, if I hit escape here and click this window and kind of drag it around, believe it or not, this is not magic, right? There's not like a little gnome that's casting spells inside of my computer. There is a way that the computer actually handles this, and it is handled through refreshing all of the pixels on your screen. In very, very quick succession, the computer goes through from the top left to the bottom right, and it rewrites the color of every single individual pixel on your screen, every single individual square. And the rate at which this happens is referred to as the refresh rate, or the frame rate, or sometimes FPS for short. The update and the draw functions that we have in our basic Lua program, going up to the previous slide, these are going to be called automatically by Love2D every single time we need to refresh the screen. And when we refresh the screen fast enough, it creates the illusion of movement on the screen. So really computers work a bit like old flip books that you might be familiar with as like a kid, where on every single page of the book we draw a slightly different image, and by flipping between them in rapid succession, we create the illusion of movement, that a character is waving their hand back and forth on the screen like this. All right, so let's do just some really basic stuff with this to show off what's happening and also point out a very dangerous thing about the Lua programming language. Let's create a variable called tracker. So a variable is going to be something in our program that keeps track of data or information. And again, there are no strong types here, so we can swap data in and out. I'm going to create tracker inside of the load function right here. I'm going to set it equal to 0. Next, inside of update, I'm going to set tracker equal to tracker plus 1 to increase its value by 1. And then I'm going to call love.draw in the draw function, and I'm going to run love.graphics.print tracker, and then to append strings and types of data in Lua, I can use ... here. So I'll print out tracker followed by tracker right here. So I'm going to go ahead and take this, and maybe in the future a nice thing would be to just offer you this code so you're not having to furiously type it. I guarantee you we will not keep up at the rate we are going, so don't worry if you fall a little bit behind. And let's go ahead and throw that into our program. And we see that tracker is rapidly increasing up at the top of the screen. So every single frame, and this will happen, I believe by default at 120 frames per second, which is what my monitor is calibrated to, it's going to increase the value of tracker by 1, and then print out the new value of tracker. And so we see this value of tracker rapidly climbing into the thousands. Now, for those of you who are a little bit more savvy in computer programming, you might notice something weird going on here. Does anyone notice something like strange about the way we've created and are using this variable?
Which variable?
The tracker variable up here. Anything stick out to us is like kind of bizarre here? Yes, I think I saw your hand go up. We haven't declared it. Yeah, was that also what?
No type.
Yeah, no type. So we don't need to define types in Lua because it's not strongly typed. But yeah, so the thing I'm trying to shuffle us in towards here is we haven't well, it's one, we haven't declared it, but it's also, how are we using tracker in all of these functions? Like, what the heck is the scope of this variable, right? Like I could declare tracker in this function, and magically I can use tracker again down in this function here. This is a very, very bizarre quirk of the Lua programming language. When we use global variables, so variables that are available to all parts of our program, we don't declare them first. We don't need to declare them first. Lua will just assume, if we're working with a variable that doesn't exist yet, that this should be a global variable. And so when we create tracker and we set it equal to 0 in love.load here, because we're just using tracker as though it already exists, Lua kind of assumes, all right, this is a global value, the whole program should be able to use it. Otherwise, why would you be typing it there? Clearly you wouldn't make a mistake as a programmer. That never happens. And then we can make use of it in both love.update and love.draw here, and we're good to go. Now, we can also limit our global variables a bit and declare them more explicitly using the local keyword. So by using the local keyword, and this is how you can declare variables throughout your program if you want them limited to a particular scope or limited to a particular function. In this case, if we put this up at the top of our file, this will limit the use of these variables to the particular file that we're working in. We're not going to use multiple files today, so this is more just a little bit of a way to organize our work and make things a little more explicit. This still kind of boggles my mind a bit. I really don't like working with undeclared global variables in Lua. That just seems dangerous. And so we're going to start by creating some variables here for the width and the height of our screen. And we're going to pick a standard 2x3 aspect ratio of 800 pixels by 400 pixels. Okay, now that we have those variables up at the top of our window, we are going to use them to set the size of the window when the game runs. And this is basically all we're going to do in love.load today. So I can do a couple of things when I boot up the game. One is I can set the title of the window. To do this, I call love.window.setTitle and pass along a string. So in this case, I called it micro-pong because we're going to make a little version of Pong today. I can also call love.window.setMode and pass a ton of information to decide how the game is going to kind of run. For today, we're going to set the screen width and the screen height using those variables we've created up at the top of our program. And then we're going to set resizable equal to false so that I can't drag or expand the window freely, and set vsync equal to true. Vsync, we're not going to get into this today. This is an abbreviation of vertical sync. It basically means, for now, that the program is going to run at a stable frame rate that matches whatever my hardware is capable of. Most of the game languages, so basically any engine or like graphics framework, yes, it'll come with the ability to flip vsync on or off like this. So if you're working with like Raylib, for instance, which is the other example we mentioned earlier, that comes with easy settings just to flip vsync on or off. Now, doing this in an API is a little bit more tricky sometimes. There's not always an immediate way to flip on vsync or flip it off. You sometimes have to go through a couple of steps of configuring things with your hardware and making sure everything's working properly. But Love2D takes care of that for us, and so that's all we need. Okay, next I'm also going to set up some font stuff. This just tells me what size text is going to appear on the screen. And so I say love.graphics.setFont, love.graphics.newFont, and then I pass in the value 30, which will be the size of the text. And some mysterious sounds are coming from the do not enter door behind me. It's a little bit disconcerting. This is all we're going to do in load today. This is all we need to really set up our game, make it work well. So rather than continuously going through from the slides to the code, I've actually prepared the full game in advance. And I'm going to switch over to that project instead. So let me briefly go over here to my window and pull out Pong full. And I think I already have that loaded up in here. So this is all the code we're going to be writing today. Just 119 lines. It's not too bad. I'm going to go through and kind of comment things in. So right now we've got the screen width and the screen height up here. We've got some other stuff that we're going to talk about in just a bit. And we've got our love.load function set up with all that information. And it looks like because love is not part of my project, I'd like to set it as global so I'm not getting squiggles under there constantly. And VS Code is failing to do this. My bad, we're going to have some squiggles here. It shouldn't hurt anything. All right. Let us return to our slides here. All right, right, so today we're going to be making the classic game of Pong, very old game, table tennis style game. The idea is 2 players, in this case one of which is going to be controlled by the computer. Each have a little paddle on the right side or the left side of the screen here that can move up and down. We have a ball that is going to bounce back and forth across the paddles. In the event that the ball crosses one side of the screen and misses a paddle, the other player will score a point. Those will be tracked up here in the top right or the top left. And should the ball hit the bottom of the screen or the top of the screen, it will bounce back and forth. This is supposed to be a GIF. It's not working for some reason, so let's find a Pong GIF to show us what's up here. This is roughly what we want to create today. So the ball will bounce back and forth across the paddles and also bounce back up and down across the top and the bottom of the screen. We're going to make a really simple version of this. All right. So the first thing I want to do is I want to create a ball on the screen. And we're going to declare this as a local global variable, bit of an oxymoron, up at the top of our file. And this ball needs to track different pieces of information. So I use the local keyword followed by ball. This will be the name of the table that I'm creating. I'm then going to set the position of the ball on the x-axis, left and right across the screen, the position of the ball on the y-axis, up and down across the screen. I'm also going to preemptively create these variables dx and dy. These stand for delta x and delta y, and these will determine how fast the ball will be moving across the screen left and right or across the screen up and down. I'll give you a while to write this down if you do want to follow along. Lua is built around this kind of fundamental thing called a table. And a table in Lua serves as an array, it serves as a hash map, it serves as a dictionary, it serves as a class. Lua just has this one thing called a table. It's very, very flexible, and you can use it in very bizarre, creative ways. And this is one of the weird things about Lua. We'll go back to the slide in a bit. So if we want to make like an array in Lua, we have a lot of different ways we can do that. One thing we can do is just create the array with a name, set it equal to some values surrounded by curly braces like this. So this will create an array of A, B, C, and D, each of which is a string. And then we can print out an element of that array by grabbing an element from the index. And again, Lua is 1 indexed, so in this case we'll print out the element B with array at 2. We count 1, 2, and get B here. However, we can also tie things in our array to basically like variable names in a class in a language like Java or something. So if I create a table here called T, and I create that with A equals 1 and B equals 2, we can access these by typing T.A or T.B. I could also do something like T equals and then set hello in square brackets as a string, and then work with this like I would a hash map or a dictionary. So I could say T at hello, that would give me 200, or I could say T dot hello, that would also give me 200. Yes, question?
Is it okay if we turn off some lights because it's hard to see the...
Oh, yeah. Ooh, I didn't pick a good palette for this. Yeah, can someone grab the lights in the back of the room? Oh, okay, is that a little bit better? We've got all but the light. That's like the biggest problem here. Can I? Oh, so this button makes it dimmer? Okay, and then maybe shut off some other stuff again. Oh, wow, okay. Is there a medium, a happy medium we can have? Something else I could try to do is just go through here and maybe create a higher contrast color for this stuff as we go. Is this a little bit easier to read? Yeah. Okay, so this is not too important for the lecture. This is just a little bit of background on Lua stuff. Tables are going to serve in place of everything, basically. And so they're going to kind of serve in place of the class that we're creating here for the ball. So in this case, I want to create a ball that has an X where it's stored on screen, a Y where it's stored on screen, and then variables that store the speed of the ball. We're going to declare a ball speed variable up in the top of our program as well. So I've got ball speed X and ball speed Y. I've separated these out since then. We could also just use a single ball speed if we really wanted to and keep those identical. But I'm going to split them out in my personal example here. Okay, now the next thing we need to do is draw the ball on the screen somehow. And so we're going to move down to our draw function in Love, and we're going to call love.graphics.rectangle. This will draw a square to the screen. We need to tell the square how it should be drawn. So in this case, we want just a solid square that's completely filled in. So we'll use the fill keyword here as a string, and then we'll provide the ball's x, the ball's y, and then the ball size to determine how big the ball is going to be. So if we head back over into our code here, we can ignore most of this. Let me go ahead and comment out this for right now, and comment out these as well. So right now, all we've got in love.draw is we are drawing a rectangle with ball x, ball y, and we've created ball up here at the top. And this is just going to be a singular ball. So we're almost using a singleton design pattern here. This is the one ball in the game. Later on, we might want to introduce the ability to spawn like multiple balls or create copies of balls. We're not going to worry about that today. We just need the one ball to get things going. And so if I run the code with that one little addition, we've got a ball right there in the center of the screen. Now the way I've initialized some of these values is a little bit weird. I've got x equals screen width over 2 minus ball size over 2, y equals screen height over 2, ball size over 2. The speed along the x and y axes, this is what we would expect. But what is going on with that? So this is how pixel coordinates work in Love 2D. And this is how they're going to work in many graphics libraries, game engines. Godot will use something very similar to this. This is kind of an inversion of the classic Cartesian plane that we're probably used to, where we've got the x-axis going along horizontally and the y-axis vertically here. When we are working in pixel coordinates, at least with Love, not everything is the exact same. The position 0, 0 is going to start up in the top left corner of the screen. So we're almost going to read through the pixels on screen like we read a book. We start in the top left, we work our way to the right, and then we work our way down. So this pixel in the top left, this would be at coordinate 0, 0, x is equal to 0, y is equal to 0. As we move to the right, pixel by pixel, the x coordinate of that pixel will increase by 1. And as we move down the screen, the y coordinate is going to increase by 1 as we get lower. And so occasionally we might have a mistake where the ball is moving up when it's supposed to move down, or down when we're supposed to move up. Keep in mind that the higher the position of the ball, the lower it'll actually appear on screen. So let's head back a little bit. All right, so I am setting things up so that the ball will initially be drawn dead center in the center of the screen. This is because when we draw a rectangle in Lua, we start from the top left pixel, and we move that many units to the right and that many units down. So if I go back to our draw call here in our code, when I call love.graphics.rectangle, x, y, size like this, it means, okay, find me a coordinate on the screen for a pixel, and we'll draw this in a little pixel art application. Start me at a certain location, and then draw me the ball size to the right. So we'll say 1, 2, 3, 4, 5. And then draw the pixels down, 5 down. 1, 2, 3, 4, 5. And so the ball's position on the screen is actually going to track this pixel right here. And the width and the height will be determined by whatever we've written in our code. That'll draw us to the right and down that many pixels. So what I do is I want to set this square to be 1, the width of the screen divided by 2. So that'll give me a location dead set in the beginning of, in the center of the screen. So if I drag this and I move it over. However, if I just set the ball's x to be halfway down the screen like this, the ball is actually going to appear to the right of that center. It won't be dead center. So what I need to do is move the ball over to the left by some number of pixels based on half the size of the rectangle. So if I move it over by half the size of the rectangle, like that, now I should have something which is evenly divided from left and half on the screen. Now this is a 5 by 5 ball I've drawn, which is unfortunate. If I made this a 6 by 6 pixel ball, then we'd be dead set in the center of the screen like that. But I'm drawing the ball in the center, moving it over by half its width in order to get it exactly where I want it. All right, cool. And so that'll draw it right in the center of the screen. We can also modify these variables if we want to change what the ball is going to look like. So let's go to the ball size and maybe set it to 30 instead up here. And now we have a bigger square that is drawn in the screen. And because when we set up our ball, we are just using this variable, it means when I change this, our ball will automatically be shifted over the right number of pixels to get where it needs to be. All right. All right. So we also need a paddle. That is going to be the other thing that kind of makes this game work, this game of Pong. And so we're going to create another table here. This one's going to be really simple. It's just going to be called right paddle. This will be the paddle that is drawn on the right side of the screen. And all this table is going to track is its y coordinate, basically how high or low it is on the screen. And we're going to do the same thing we did with the ball. We're going to set y equal to the height of the screen divided by 2 minus the height of the paddle over 2. The paddle height and the paddle width are going to be things that we define up here along with all of our other local variables. So paddle width will be 15 pixels across, and the paddle height will be 100 pixels across. And then once we have stored this information in a table, we can then draw the paddle to the screen. We're going to use love.graphics.rectangle, fill once again, screen width minus the paddle width, right paddle y, paddle width, paddle height. So this rectangle will take the type of rectangle we want, the x coordinate, the y coordinate, the width, and the height of the rectangle, like that. So the only coordinate that's really tricky here is kind of this x coordinate. We're using screen width minus paddle width. The idea here, if I clear out things in my little pixel environment, is if I've got a paddle that, let's say, is 2 pixels, and I want to draw this on the right of the screen, well, I want this pivot point in the top left to be 2 units away from the right side, so that when I draw the rest of the rectangle, starting from here, it's perfectly flush against this side of the screen when it's drawn. So I'm moving it over a little bit from that side to get it perfectly flush. So let's head back into our code here. And underneath, or sorry, right above where we are drawing the ball, I'm going to draw the paddle using that code from the slides here. So love.graphics.rectangle, fill, screen width minus paddle width, right paddle y, paddle width, and paddle height. And let's go ahead and run our code again. Oops. And, there we go. All right, and so we've got a ball in the dead center of the screen, and we've got our paddle over here on the right side of the screen. So we've got our 2 objects that are being drawn. And our ball is looking a little bit large, so I'm going to go ahead and set the size of the ball back to 15 pixels. That looked good when I was putting this together earlier. Back over into our slides. All right. So right now we are just drawing things in black and white. We can change the color. The way Love does this is pretty conventional. I prefer Raylib's way of doing it better, but you have to take that class to find out how it works. What we're going to do is, before we draw the ball or the rectangle, we're going to tell Love 2D what color to work with. So Love 2D is in charge of drawing all these rectangles. We're drawing balls, and we're drawing paddles in the form of rectangles. And right now the default color is white. We can kind of switch things up and tell Love 2D to use a different color with love.graphics.setColor, and then 4 arguments. These 4 arguments will be the amount of red, the amount of green, and the amount of blue that appear in our color. The final value is called A, or alpha, and this is kind of the transparency of our color. We're just going to use a value of 1 today, so everything is fully opaque. We can't see through anything. But if you wanted things to like appear in front of something, you were using like a window or something in your 2D game, you could reduce that value down. You'd have a square you could then see through. So let's back up into our code, and I'm going to use love.graphics.setColor, and let's use 0 for the red, let's use 0.5 for the green, and 0.5 for the blue. And let's head into our terminal and draw that. And now we have this nice teal color for the ball and the paddle. Now, this can be switched at any point in love.draw. So if I want to draw the rectangle one color, like this, and then draw the ball a different color, I could call love.graphics.setColor again, ahead of where I'm drawing the ball, and then change the color here. Let's say we'll use 0.5 for red, 0 for green, and 0.5 for blue. And oops, sorry, I'm using the wrong shortcuts on my keyboard. And now we have kind of a purplish colored ball and a teal colored paddle. I want to make these kind of neutral, so I think I'm going to actually make the ball white. Now, all of these values go from 0 to 1, 1 being the maximum, 0 being the minimum. I'm going to set each of these to 1. When I combine the maximum amount of red, green, and blue in a color, we get white. We get the pixel fully lit up to its maximum extent. And then I'm going to use a slightly darker color for the paddle. I'll say 0.5 across the board. That'll give me kind of a grayish color. One more thing I can do is I can set the background color. So what's going to appear behind everything that we are rendering to the screen. And for that, I'll use the 0.5 for the green and the blue, like we did before. All right, and so now we've got kind of a gray paddle, a white ball, a nice turquoise, calming ocean green color for the background. And let me actually increase the paddle color a bit. It's a little bit too dark for my liking. Maybe to 0.75 across the board. There we go. It's a little bit different from the ball, but still fits in. All right. Next, it is time to move the paddle. And this is going to be pretty easy to do. The paddle is a table up here, and it tracks its Y position on screen. This variable Y, this is used way down here in love.draw to determine where we're going to appear, up and down on the screen. So by changing this Y coordinate, we can modify where the paddle is ultimately going to go. So if I were to go here into my update function, and I were to set the paddle dot Y, and I were to set that equal to paddle dot Y plus 1, and I believe I call this right paddle actually, so let me change this to right paddle. Like that, and I were to run the game, my paddle is going to move down the screen slowly over time, like this. Every single time the game refreshes the screen, which will happen about 120 times per second right now, the paddle's Y coordinate will increase by 1, and that new value will be used to draw the paddle in a different location on the screen. So this is the basics of how we can move things around in 2D. Now, there is a bit of a problem with how we're doing this, and that is depending on how fast my game is running, what the frame rate is, the paddle is going to move across the screen in different speeds. So let me head over to this slide right here. We're going to go in a little bit different order. When I am running a game, I might have different frame rates depending on hardware limitations, software limitations, who knows what. So I might be updating my game 60 times a second, 30 times a second, a buttery smooth 15 cinematic frames per second. And if we are running the update once per frame, it means the smoothness of our game is now going to determine the speed at which things go across the screen. Here we have a little text example where 60 FPS, 30 FPS, and 15 FPS are all moving across the screen at the same speed from our perspective, even though they're being updated differently. As things are written now, if I reduce the frame rate, our paddle will actually move down slower across the screen, or move faster across the screen, depending on what this is. So if I am running the game at 60 frames per second, and I am moving the paddle 1 pixel per frame like this, then that means every second I'm going to end up moving 60 pixels total. Whereas if I'm running at a frame rate of 30 FPS and I move the paddle, again, 1 pixel per frame there, I'll only be moving 30 pixels per second. And we don't want this. This causes problems all over the place in game development. Even some large AAA games still struggle with this idea of frame rate independence for some reason. If you ever played the original Dead Space on PC, you could modify that in order to boost the frame rate to 60 FPS, and it would cause the physics engine to completely break down. Things would fly through walls, and it was because of this issue. It's because the developers hard-coded their game around an assumption that it would always be running at 30 frames per second for all eternity. Now, Love provides us with a way to get out of this in the form of this argument that is passed to the Love update function called DT. This stands for delta time, and this is the period of time that has passed since the last frame, or I should say the length of time it took to render the last frame. And so by multiplying our speed by this value, we can make sure that things are always moving across the screen at the same rate, regardless of how fast or slow the game is running. So if I am moving, let's say my paddle, at 10 pixels every single update, and I'm doing that for 2 seconds, and my game is running at 60 FPS, well, I can multiply that by dt, which in this case will be 1 over 60 FPS, so the time it takes to render a frame would be 1 over 60. And this term right here, these would cancel each other out. And I would end up moving at a speed of 10 for 2 seconds, meaning I move 20 pixels over the course of those 2 seconds. If my game is running at 30 FPS, well, this dt will be 1 over 30 to reflect that as well. These terms will be canceled out again, and once again, I'll be moving 20 pixels per second. So whenever we are moving something, changing something over time, and this could be affected by variable frame rate, we always want to include dt in our calculations to multiply things by that to make it frame rate independent. So if I head back over to here, let us now say right paddle plus equals 1 times dt here, and I'll go ahead and wrap these in parentheses. And this will end up moving our paddle a lot slower. It's like barely moving. Because again, this is going to be 1 over 120 by default. So this is going to be moving really, really slow. We can increase the speed at this point to something like 100. And our paddle should be moving faster than before. There we go. Moving faster, and this will be completely frame rate independent now. All right. So we head back over into Unity here. And go back to moving the paddle. Let's use this right here. We need to tie the movement of the paddle to keyboard input from the user's standpoint. So when we press a key down, the paddle should move in one direction. When we press another key down, the paddle should move in the other direction. Love provides us a way to easily scan for keyboard input in the form of this love.keyboard.isDown function. We pass the name of the key we want to detect in single quotes like this. So if I want to press down the W key or the up key on my keyboard and move the paddle based on that, I can use this line of code right here. If statements in Lua work a little bit interestingly. So for one, there are no parentheses around them as you might be used to in other languages. We're going to use the OR keyword in place of the double pipes that you might be familiar with. And all of the if statements need to end with a then keyword. So if this condition is true, then this is going to happen. I really don't like this. It's really annoying, but it's Lua. It's yet another programming language. And so what we're going to do here is if I'm pressing down W, I'm going to set the right paddle's Y coordinate equal to the current coordinate minus paddle speed, this will be another variable, times delta time to make it frame rate independent. So if I'm holding down W, continuously subtract from the Y coordinate, and that'll move the paddle up towards the top of the screen. If I'm holding down the S key or the down key, then I'm going to add to the Y coordinate instead and move the paddle continuously down the screen. So let's head back into our code and let us enable that. And use the wrong comment for that. And I'm just going to use up and down on my keyboard for this example. And when I run the game, I can hold up to move the paddle up and hold down to move the paddle down. We got a new issue here, and that is the paddle. Oh, actually, no, we don't have this issue because I solved it earlier when I was writing the code. Let me head back to the slides here. If we wrote this thing the naive way, if I held up on my keyboard for long enough, our paddle would actually go past the bounds of the screen. We would go too far up and leave the screen, or go too far down and leave the screen, and that wouldn't be good. We want our paddle confined to the screen up or down here. So quick way of fixing that is I'm going to, when I move the paddle up by subtracting from the Y coordinate, I will always end up setting the paddle's Y coordinate to the maximum of 0 or whatever coordinate I would have updated it to with the movement method. So if I go back into the pixel art program here, the idea is this little pivot on the paddle that determines where it's drawn from, I never want that to be less than 0, which will be at this point in the screen. If it's less than 0, that means part of the paddle is actually being drawn way up here where I can't see it anymore. I then do the mirror of that down here where I'm sending the paddle down. I set it equal to the minimum of the screen height minus the paddle height. So this will be wherever I draw the paddle with the pivot, its height to ensure that it is flush against the bottom. And then the new coordinate that would have been changed by the movement operation here. So by including this maximum and minimum, I can bind the paddle to the screen, up and down. All right. Now we only have 10 minutes left. Maybe we can go a little bit over, if y'all will bear with me. I think we can at least get half of Pong working in that time. We'll see here. Okay, let us move the ball. So the ball is also tracking these dx and dy variables. These are tracking how fast the ball is moving across the screen on the x-axis or up and down the screen on the y-axis. All we need to do to move the ball is use that value and continuously add to either the ball's x or the ball's y coordinate. Once again, we're going to include delta time in our calculation here to make things frame rate independent. So let's go into our code. Let's comment this in right here. Ball x equals ball x plus the change in ball's position x times delta time, and same thing for the y coordinate. Now the y and x speed, these are just variables that I've created up at the top, and we're going to set this to 50 along the x-axis and 100 along the y-axis. And so our ball should move continuously downward in a diagonal direction when we run this. And there it goes. It's drifting off into space, and once again, it is going to leave the screen. So this is not the behavior we want. We want the ball to bounce off the bottom of the screen, and that is actually a lot easier to achieve than you might think. All we need to do is check to see if the ball has either gone too far up or too far down. In the event the ball has gone too far down, so the coordinate of the ball's pivot plus the size of the ball is greater than or equal to the screen height, then we're just going to snap the ball to that position, so move it back up so it's on the screen, and then we're going to set the ball's y directional velocity equal to negative of whatever it currently is. So if the ball is traveling down and hits the bottom of the screen, we'll flip the y velocity and it'll start traveling back up instead. And we do the inverse of this for the top of the screen. If the y is less than 0, then we set the y equal to 0, and we set, again, the ball's y velocity component equal to the negative y velocity component. So let's go ahead and add that into our game right here. Run this again. The ball is traveling, it reaches a point too low, and we reverse that y velocity, and now the ball is traveling back up again. Well, now the ball is going off to the right side of the screen. When the ball travels off the right side of the screen or the left side of the screen, this signifies that one of the players has made a point. We'll track that later, but for now, we want to make sure that the ball just kind of resets to the center of the universe whenever this happens. We're going to do that with a similar piece of code right here. And I'm going to speed through this a bit, unfortunately, because we're running out of time. My apologies. Basically, if the ball's x is less than 0, so it's gone all the way to the left side of the screen, or the ball's x is greater than the screen width, gone all the way over to the right side of the screen, we are just going to set the ball x and the ball coordinate back equal to the screen width minus the ball size over 2. And let's go ahead and reverse the direction of the ball. So we'll say ball.dx times -1 for both of these. Actually, I could just use negative in front. We'll make that a little bit cleaner here. All right. Run this code. The ball moves. We bounce off the bottom of the screen. We travel to the left. We go too far, and we appear on the other side, reversing our x direction. So now we're traveling to the left side of the screen. All right, cool. So I think the last thing we'll try to get to is we'll try to get the ball bouncing off of our paddle on the other side of the screen here. Now, to do that, we need to talk a little bit about intersection in 2D game development. And the math is pretty simple for this, but it's unfortunately a little bit tedious. Let's imagine two squares that are being drawn on the screen. One has a pivot of 0, 0, so this would actually be in the very top left corner. And the other has a pivot of 7, 0, so it's drawn 7 pixels over like this. Both of these boxes are going to have a width of 5 pixels and a height of 5 pixels. In order for the boxes to be overlapping in our program, the following 4 conditions all need to be true. So first, corner 2's x needs to be less than corner 1's x plus corner 1's or box 1's width. The way to interpret this first condition is if I'm box 1 and I start at 0, 0, and I'm reaching over to the other box, I've got a width of 5, my arm is 5 pixels long to reach out and grab it, then my length should cross over where the other box begins. And in this case, that condition isn't satisfied because if I start at 0 and I reach over 5 pixels, I'm only going to get to pixel number 5. I'm not going to reach pixel number 7 here and be able to clasp on to the box there. So this condition fails, and we know immediately, just from checking that one condition, these boxes are not overlapping. If we go to the other case here, so we've got a box that is now drawn at 3, 3, so it's over 3 pixels and down 3 pixels. If I imagine myself from box 1's perspective, if I'm reaching over to the left, well, if I reach over 5 pixels, I'm going to cross that 3rd pixel here where the other box begins. I need to perform the same check from the y coordinate of the box. So if I'm at the top here and I reach downwards, well, if I reach 5 pixels, And the box here begins at 3. Mine 5 pixels is going to stretch well over where the 3 begins, and I'll intersect there. We basically then check the exact same thing from the other box's perspective. And because this box is to the right of the box, all of those are going to succeed trivially. And so all of these conditions succeed, and the boxes are considered overlapping. So we are just going to perform a condensed version of this. We're going to say if the ball's x plus the ball size is greater than the screen width minus the paddle width, and the ball's y plus the ball size is greater than or equal to the player y, and the ball's y is less than or equal to the paddle y plus the paddle height, then, so for satisfying all these conditions, we will reverse the direction of the ball, and we will set the position of the ball to be flush against the paddle right here. So let's go ahead and handle the collision right there with that big, ugly chunk of code. Now, if we move the ball down and move the ball up, we can bounce off the paddle and save ourselves from it going across the screen. We've only got 4 minutes left in this seminar. The rest of the work involved with this is really not that much more complicated. So I'll quickly speed through it to show you what we would have had. We're going to perform the exact same logic with a left paddle. That left paddle is just created here as a separate table up in the start of our code. We are going to draw that left paddle with the exact same line we used for the right paddle. We're just going to draw it on the left side of the screen. And then I have a little AI function here. Where did I hide that? Which is going to move the paddle up and down, adjusting its y-coordinate, depending on whether the ball is higher or lower than the paddle. And when we make those 3 changes, we will have a functional game of Pong. And really, we can make the ball move a little bit faster here to make things a little spicier. Let's do 200 for the x speed and maybe 200 for the y speed. There we go. Blink. And our AI is very kind of optimal here. It's going to adjust its position instantly to meet the ball. So we might need to make things a little more fair for us as players, because I don't think it can ever lose here. But yeah, we've got a basically functioning version of Pong here. So sorry for running out of time. I was a little bit too ambitious, I think, in the construction of this lecture. But thank you all so much for coming. I hope this was interesting. If you have any questions, I'll be around for another while. Yeah, feel free to come up and talk. And yeah, thank